So in the last lecture, I introduced Newton-Raphson method, and today I am going to describe how it can be used to calculate matrix inverse. Just to repeat the notation, the problem is Ax equal to b, which is solved as x equal to A inverse times b. So it's an iterative method, and in any iterative method, you have to start with some initial guess and converge towards whatever the answer is going to be. And the description or the parameterization of the inverse is in terms of what is known as a residual term. Okay? How far you are from the exact answer, and that in some sense is related to the overall error of the algorithm, and you want to shrink it to 0. So here, let me define the initial guess is say some x 0, or right now let me first do with the matrix problem. I will come back to x a little bit later. So initial guess for A inverse is B0, and residue for this guess is defined as R equal to I minus B0 A. So this B0 has slowly to move towards the exact answer, which is A inverse, and this is a parameterization of how far you are. So now I can construct a quantity which is quite easily rewritten as a power series convergence towards this final value where R goes to 0, and that can be evaluated in some sense is taking the inverse of whatever the term is there, and by construction that is A inverse B0 inverse, standard rule for matrix inverse, and this is equal to 1 upon I minus R, and you can write this now as geometric series. So now I define a partially converged result, which is B of R is truncated version of this series multiplied by B0. The extra B0 I can just obtain by taking this B0 inverse and shifting onto the other side of the equation, multiplied by B0 from the right hand side. And this means that if I take the full series, I will get A inverse. That's just this result. I minus R is equal to B0A. B0A inverse is A inverse times B0 inverse. Is this 1 upon I minus R. It's just rewriting this equation. The same thing. If you want to write I minus R in power minus 1, it's identical. There is no difference. Okay. So now I give the answer of how Newton-Raphson method goes towards this result, and that was obtained by the recursion relation, where the quantity which was iterated was, let me follow the same notation. This is the matrix version of the Newton-Raphson approximation, or not approximation, but convergence toward the solution. So when R goes to infinity, this stuff immediately says that you will get A inverse. Okay, because I have defined this B infinity is A inverse. But let us evaluate this and see how it converges. This is just one iteration. So now I'm going to substitute, I know what is BR, so and minus again this whole factor and times B0A and then another factor of this times B0. I'm just substituting the definition. But what is B0A? This is I minus R. And what is this product? It's a well-known identity in summing up a geometric series, which is I minus R raised to R plus 1. Okay, so that now gives me the simplification. When this is I, it basically just cancels this half of this term, 2 becomes 1, okay, the first term. But the second term remains. So this is up to R to the power R, V0 plus let me just keep it as it is. So what I have got on this side is a series which just continues to higher order. Up to R raised to R is here. This starts from R plus 1 and goes up to 2R plus 1. and that is the power of the Newton-Raphson method. One iteration took you from order r to order 2r plus 1. It's far more powerful than a geometric series. So just convergence for geometric series basically goes rise epsilon to the power n, and n keeps on incrementing one at a time. But what you are seeing here is a second order method where how does it converge? It's epsilon raised to power 2 to the n. So this is way ahead of this, and that is what I described last time, that if you have one iteration which is correct to one part in 1,000, next iteration it will become correct to one part in 1,000,000. It's not going to be 1,000 plus 1.
Small r is not the number of iterations.
It's not the iteration, it's defined by this identity. Epsilon is whatever the error, r is this residue, how it is going to go down.
What's the value of small r?
You can take it as a number of iterations of Newton-Raphson method. That's what it is. One iteration will take you from Br to B of 2r plus 1. It's not the order of truncation, it's the number of iterations of the method. So this is something which well, can be used quite productively to calculate inverse of any type of matrix. Doesn't have to be following into some particular category, though we'll come down to using it for certain type of sparse matrices because they are the one useful in some practical problems. The identity is far more general. Now let us come back to solving this problem. This is just solving this inverse, but what I am interested in is in calculation of actually x. Okay. So iterative solution is xr equal to we just defined it to be this, whatever is the current value of the inverse. Of course, when it goes to infinity, you will get the exact answer, but at some finite stage, this is what you can calculate. The question is, how does this converge? Its convergence of this is not the same as convergence of B. We'll quickly see that, and you actually lose the advantage which came over here. This converges only geometrically. Yeah.
Error. So we choose a minimum and then we define error. So what if the error magnitude is like greater than 1? Won't the error just multiply?
If the initial guess is not good, the iterative methods are useless. You have to start somewhere sufficiently close to the solution. You have to find the range or the domain of the solution where this quantity, whatever the residue, is less than 1 in the norm. Because everything will involve powers, and if the norm is not less than 1, you are not going to go anywhere.
Using Newton-Raphson and find PR with the sufficient higher iteration, we get A inversion. When we use the Newton-Raphson method for matrix,
Yeah.
we get A inverse. Why can't we directly multiply that with the B to get X? Again, why do we involve an iterative process for X?
If you want to iterate this particular method, you have to do matrix multiplication, okay, which are far more expensive compared to matrix times a vector multiplication. Okay, one of them says size is n, matrix multiplication will take you order n square, but matrix times a vector multiplication is order n. Just one row and one column. In the other case, you have to calculate for each row and each column, etc. The 1 power of n complexity is more. Yeah.
This iteration also involves like iteration of PR.
No, that is the point. You can calculate this XR only using matrix times vector iteration and not matrix times matrix product. You can evaluate this if you want, but there are matrix times matrix product which are much more expensive in terms of computational effort. So the result for this is quite easy to write down. That the convergence of this, what is x of r plus 1? It is just xr plus this correction, which is again some deviation from the solution. Can check it out rather easily by again putting in the expression of what is b0 times a, and that is written somewhere. I have to factor out. So there is a br, and I have to simplify this result. So let me see how does it work. So xr 1 this and this plus b0b, and what is this quantity? This is r. xr was defined as this. And plus this last term, and then you can see that this is the same series but one extra power. So that is by definition this. Where? Yeah. This was the definition I worked out in the last time for a inverse. This is a Newton-Raphson inverse iteration. It's a matrix version of it. Write down, last time I wrote down xi plus 1. This is what I derived in the last lecture, if you have the notes. The Newton-Raphson method for A inverse is this particular result. This is a matrix version of it. Only thing which I chose cleverly is the order of these terms, because last time I just derived this for numbers. But matrices don't commute, and that's why I have to take a particular order, and this is the answer. This is how you use it, and it gives this rate of convergence. So if you iterate x by adding these terms, it goes from order r to order r plus 1. It is only a geometric convergence. It is not as good as this. But the advantage is, in iterating this result, what you are doing is only matrix times vector multiplication. Okay. And so you gain something in terms of the size of the matrix, but you lose something in terms of how it converges. So now let us give a bound of this quantity in terms of its convergence. And which is given by the norm of this particular object. At some iteration number, and this is the exact answer. Norm I can, I'll put it a little later, but yeah, because the identities actually hold even without the norms. What is this quantity? Well, we defined it over here, and we just rearrange the terms a little bit. XR plus 1 was equal to XR, and there was a minus x, so this is XR minus x, which is the identity part, the first one. And what is this quantity? B0A times XR, which is the first term, and B0 times B is nothing but b0 times a times x, because b is equal to a times x. Purpose of rewriting it, it gives you an iterative result. R plus 1, this is R. So now I can go down all the way. No problem there. And one more step, because I know what is x0 minus x, and that happens to be, there's a negative sign. Because x is directly here, there is just a minus sign, an identity for that. What is x0? x0 is nothing but b0 times a times x. Either this or this, whichever way you write it. So this gives me a straightforward result in terms of what can be called a fractional error. Remember, these are linear equations, so the overall norm of the vector x can be changed around, doesn't require fixing, but compared to the norm of x, how much you are able to reduce. So you can write it now, you can put a norm sign over here, and that is, well, I have to put a norm of this, some kind of norm, but well, so, and r plus 1 I can remove 1, etc. This is some version of the Cauchy-Schwarz inequality, because when you multiply a matrix times vector, you have a contraction of an index, some kind of dot product. You remove it in terms of the magnitude of the two factors. Well, I removed one r on this side. That's okay. So now we have a quantification of the fractional error. I can just define this. Whatever this quantity is, some power, it will go down exponentially. You need this number to be less than 1, otherwise it's not going to converge. And so that gives the standard criterion that you want to put this thing less than epsilon. How many iterations you need? Log of 1 over epsilon, because r is in the exponent. And you can rewrite it as in many different ways in terms of normalizing various things, so I can just write one convention. So when you normalize this matrix to magnitude 1 by overall dividing a constant, you can rewrite the various magnitude which appear. The size of inverse becomes the condition number, the ratio of the largest to smallest eigenvalue. The largest eigenvalue I put 1, and inverse will then give the smallest eigenvalue, which I can rewrite as this theta of 1, and the norm of this quantity will be now theta of kappa times norm of B. I have to put a norm here. Because this is just A inverse times B, whatever it is. So one can write all these things more formally in terms of these eigenvalues of various quantities. You have to pick some normalization, but once you do that, the condition number starts appearing everywhere. And it's buried inside indirectly here. When you say how many iterations are required, it will depend on the norm of this matrix. So now comes the next question. How are you going to choose this initial guess? You have to find something which guarantees a convergence. This is you need something which is easily known in terms of the definition of the problem, and also where whatever multiplications, etc., you are going to do can be done without too much trouble. You cannot take any arbitrary complicated function, because then the whole optimization machinery will break down. And people figured it out. So there is a convenient choice is the Hermitian conjugate of a dagger multiplied by some constant. How does it help? Well, one thing that happens is in this quantity, you have a dagger A, which will become a positive definite matrix. So all its eigenvalues are positive, whatever this thing is. And if you can bound it nicely, it's an identity minus something positive will be less than 1. Okay. Alpha has to be a positive number, I'm assuming that. Now, how will you choose alpha? Well, you try to make alpha as large as possible, because you want to get identity minus a dagger A. The more you take it away, it will converge faster. So alpha should be maximized. But something else happens, that if you take the largest eigenvalue of a dagger A, so let me take eigenvalues of A dagger A are positive. So it will have some largest eigenvalue and smallest eigenvalue. And with all this convention, with what you call ratio, become kappa square, because there are two factors here. Kappa was the norm of eigenvalues of A, here it gets squared. So now you can ask what happens to this number. There is the largest eigenvalue and there is the smallest eigenvalue, everything is in that range. The largest eigenvalue will help in the sense that alpha times the largest eigenvalue will tell you how much you will shrink. Actually, no, not on the other side. That's so well, max of I minus B0A will be one minus I took alpha and lambda min. This is the largest value for running over the whole range. But then there is a minimum and sure you want to increase alpha so that this becomes smaller, but what will happen over here, it can go and hit a negative -1. You cannot afford to go this to the negative side beyond -1 because it's just a norm. You have to restrict it on both sides. And the base choice is where this number is exactly equal to minus that number. Then both of them will have same value, one will be positive, the other will be negative. Anything less, it will be less efficient. So and it has explicit solution. So you keep on decreasing alpha till the norm will be dictated for some time by this, but then it will be dictated by that, and you want to make the base choice, then there is an alpha here also. And there is a solution. So that gives the complete specification. Alpha is this, B0 is that number times a dagger, and then this whole thing will converge up to some power, and which can be formally written down, and that gives the rate of convergence of the algorithm. That gives the complexity. The operations. That comes from this iteration formula. The 2 is because I'm multiplying vector times matrix once here and second time here. Okay. And this is a matrix vector multiplication. And now R I have to rewrite in terms of all these numbers because it's governed by some accuracy. So let me put it a bound. So to reach I basically obtained this answer, and whatever is over here, I want to find a bound epsilon over that. Delta x is just the difference from the exact answer. The number of iterations R will be needed is I can put an order symbol because this is approximate counting. So that gives the efficiency of this Newton-Raphson method for calculating the inverse of the matrix. Okay. If you compare with whatever I had mentioned last time about the conjugate gradient algorithm, that also depended on how much is the effort for matrix vector multiplication, what is the accuracy, and there is a factor of the condition number. So matrix vector multiplication, that number is the same as conjugate gradient. Log of 1 epsilon is also the same, but this factor is not. Okay. So that was used most of the time for A, which was positive definite. And in that case, there was a root kappa. If matrix was not positive definite, it will be kappa, but this is kappa square, which is worse than both of them. So this is and that is something which cannot be avoided. In some sense, it's a penalty coming from the fact that in conjugate gradient you are decreasing the distance from the solution also in a geometric progression, but it was automatically ensured that the successive directions are all mutually orthogonal. In this particular case, yes, you are iterating with some powers of this matrix, but you have not put in that orthogonality constraint. And that is where the method slows down. So, orthogonality. Conjugate gradient does better precisely because this orthogonality helps a lot, but you want to calculate the orthogonality of vectors, you have to take dot products and make it equal to 0, and there was no way to calculate dot product easily in superposition, so you wanted to get around that, and you achieved two of the parts which are same, this vector multiplication and the convergence, but you paid some price somewhere else. And the advantage which came is that now you don't have to calculate dot product. So as long as you can do this matrix vector multiplication efficiently, you can do the superposition. And so if that is something which you can do, and that is where the algorithm uses the quantum feature. Everything what I did over here, there was nothing which depended on quantum dynamics. And when I say that now I'm going to do superposition, that is the place the quantum advantage is going to come in. And what it does is, from the dimension n of the matrix, you go to log n number of qubits. So the other factors will remain, this will remain, this will remain, and instead of dn, which was a measure of this, CD is the sparsity of the matrix. So, okay, I have to write for sparse matrix. doesn't work for any general matrix. It has to be a sparse matrix. Then we saw, depending on the matrix structure, you can reduce from capital to log n, and these tricks were all what you call same as in case of the Hamiltonian simulation, where you did this block structure. Efficiently calculated this matrix element given some index. It's another word which was used was graph coloring to identify various blocks and do this matrix vector multiplication. They're all the same as for what you call Hamiltonian. So this gives a generic counting of the how good the algorithm is, provided you have several conditions satisfied, and it all boils down to finding a method where you can do superposition, which will reduce this capital N to log n. And you have to find a good algorithm which allows you to do it everywhere. So it didn't work in conjugate gradient, so we looked at another method where it can go through. I mean, it's not necessary that this is the only method. You can try finding some other version where it works, and that is kind of open to various trials and errors. But one thing which I mentioned last time, I can write down explicitly, where the algorithm is not so good, and this is algorithm which is quoted very often, doesn't work so well, which is it gets a reduction from n to log n, but the epsilon part is not so good. This is kappa. No, I think this has to become log n because it does use superposition. But this power law is not good, and the way it works, it's it arrives at this result by using the phase estimation method, which is part of Shor's period finding algorithm, and it essentially takes this matrix and treats it as a Hamiltonian and find its eigenvalue as various phases, etc. So because the Hamiltonian has nice structure, you can do superposition and get it down to log n. But the epsilon doesn't come out with the right behavior. It is much worse than log of 1 over epsilon. So this is one input, and oh yeah, forgot one thing. I have to give a prescription for figuring out this lambda max and lambda min. I just said that it is given by eigenvalues of a dagger A, but how, for a general matrix, how do I know what it is? Most of the time it is unknown. So there are, yeah.
Divided by epsilon. Log n divided by epsilon.
No, they are separate things. Epsilon is in the denominator of everything else. The same different products. Yeah, just like this. It's a independent product coming from different places. So how are you going to estimate these eigenvalues? Because kappa in general is unknown. There are various tricks that are used. One of them is called preconditioning. It basically said you want to bring it down because the power law dependence is going to hurt all the time. And again, this is a technique independent of whether the algorithm is quantum or not. It is used generically in the iterative method. So you simplify the problem such that the range of this eigenvalue becomes smaller. And in this particular case, it means that you find a approximate inverse for the matrix. So let me call that whatever this A tilde inverse, it has to satisfy a condition that it has to approximately invert this in whichever way you can think of. And top of that, it must be efficiently calculable. It can even be, say, a diagonal matrix, whatever it is. If you can do that, then because this is an approximate inverse, the range of eigenvalues of this A tilde inverse times A is smaller than this value kappa. So that is what happens. And for certain problems, there are guesses of this approximate inverse which you can make, and you can improve the performance. But that is always problem specific. You have to know the structure. So this is one point, and then other point is, well, you did all the tricks, etc., but you still have to estimate this eigenvalue, otherwise you can't find this alpha initial value. So it's not even estimate. And give me remember that the matrix we already turned into positive definite, and we were looking for alpha as large as possible. If you don't reach the best value, you can alpha can be a little smaller, but then you can still find that the algorithm will converge. The closer to you get to the best value is desirable, but you can say that I will find an upper bound on alpha, which means the algorithm converges. It may not be optimal, but it should be easily calculable, whatever this thing is. And there are well-known techniques in linear algebra for finding bounds on the eigenvalues. Okay. So there are two expressions which are based on the Frobenius techniques. And I will just write them down. One of them is this quantity where this denominator is nothing but trace of a dagger A. You are trying to find bound on the eigenvalues. Well, sum of all the eigenvalues is trace of a dagger A. And they are all positive, no cancellation. So it will give you some result. It's not going to be very tight, or there's another expression which is also used, which is I have to write some maximum somewhere in this quantities. Yeah. It's not just ij summation. So in some sense, you look at a row, and this is the largest element in the row, and this one will be the largest element in the column. They're just these indices are interchanged, and if you do that, then you'll get the quadratic expression, which also gives an upper bound. But these are known from linear algebra analysis, or what is good and what is reasonable. But point is that you have to do this to be able to start the algorithm. So this, how will you calculate the generically it requires a summing up over all the elements, which is too much. It will be just performing these sums will be looking at all the elements in a particular row or column, etc. And because of lots of 0, it will be order d times n, but that is too much because I don't want anywhere n appearing, it will become log n. But now under the same assumption that the matrices are broken down into block structures, you don't have to look at all over the place. You look at one block, find the value, and it will work everywhere. Okay. So under that condition, this also can be obtained, and it is simple enough to implement. Yeah. Okay. So I have to say. I will write down. That A tilde inverse is not exactly the same as A inverse. It is some approximation. Okay. So now I take that equation and multiply by A tilde inverse on both sides. I'm assuming that A tilde inverse is efficiently calculable, so this does not require too much work. It's like a matrix vector multiplication. But the condition number of A tilde inverse times A will be smaller than the condition number of A.
So the kappa is the condition number for
Kappa will be now become the condition number of this new object. And this kind of inverses can be found, or rather they are even tabulated in many of the problems involving partial differential equations, where the couplings are kind of nearest neighbor. So the matrices have a what called a tridiagonal structure, and for the tridiagonal matrices, there are good cases of approximate inverses. But the statement is more general than that. But you have to look at the problem structure and see whether there is a good approximate solution available or not. There is one more expression which I required for completing this calculation. So for that is for finite precision is similar to what I worked out in case of Hamiltonian simulation, that you do the calculation with a finite number of register size. It's not arbitrary real numbers, some truncated integers, and how many decimal points you will keep in the calculation to control round of error. So there is I should put a lower bound. So this is omega. You need at least this many bits in the register, but the dependence on error is logarithmic. And yeah, to be more precise, all these norms are there, so it should be multiplied by norm of x for the sake of completeness. So that is the expression. It's the same thing which was valid for Hamiltonian simulation, except the number of iterations is now r instead of whatever number was used for the power series truncation. Okay. Yeah, so this is as much as I want to discuss this matrix inverse problem. Then the other applications of Newton-Raphson methods are there in many different kind of problems, all where you need what you call fast convergence in terms of the iterations, and well, I don't think they have been explored in enough detail for many matrix related problems. All I discussed were, one was the exponentiation of a matrix and another is the inverse of a matrix. But one thing which you will find in books of numerical analysis is the use of Newton-Raphson method to calculate square root. If you look at the what you call the scientific calculators of many different types, the two power expansions or power calculations are very commonly listed. One of them is reciprocal, another is the square root. Of course, then there are exponentials and sine and cosine, etc., which can be done in different ways. So the question is, how does a computer calculate a square root? Okay. Again, you can say that I can make the range of a square root bounded, and then by just shifting the decimal points, and once it is within a certain range, I will do a polynomial approximation. So that's okay. It's same thing I illustrated for 1 over x as well, and it kind of works as well. But there are various other tricks about calculating the square root, and the Newton-Raphson method happens to be one of them. And there are also many very interesting algorithms for calculating log very efficiently. How will you calculate a logarithm of a number on a computer without knowing well, complicated things? These are tricks you find in numerical analysis books. But let me illustrate the square root part, because I think it can be useful if some solution is formulated for matrices as well, but nobody has found a good algorithm for calculating a matrix square root. Okay, so the problem or the new feature which appears for these other functions like square root is a multi-valued character. For a number, there are two square roots, one positive and one negative. And so the iterative algorithm will converge either to one solution or to the other solution, or may not converge at all. And which solution you obtain depends on where you started, the initial guess. If you are close to one solution, it will converge to that side. So this extra feature which appears, it was not there for a reciprocal, because reciprocal is a one-to-one function. Given x, it is specifically denied. So how do you calculate square root by using this particular equation? You have to find a function for which f prime can be calculated easily, but after you put in various quantities, you should be only using addition and multiplication, nothing else. So the version which people figured out, which works for this function x, it looks something like a minus x square is this, then what is the square root? Then x is actually 1 over square root, so it is obtained as find the 0 of this and multiply by a. A is known, and this is what you want to calculate. So this is cleverly designed by doing that when you calculate the derivative, it will give a positive power of x in the numerator. Everything else disappears, and then you have only addition and multiplication left. So you have to do a little exercise. So the iteration will be x of n plus 1. Then derivative of this is 2 divided by x cube. So some result comes out of this particular type. The point is that this can be calculated using only addition and multiplication. And then you let it converge, which I just wrote as x infinity, multiply by power of a to get a square root. And this, again, it's a Newton-Raphson method, so it's a second order method. You need 2 or 3 iterations and you are done for the whatever 8-bit or 10-bit precision which you, not bit, 8 or 10 decimal point decision which the calculators give. Nothing more complicated than that. So this is all fine. The question is what is the place where it converges? So you can easily see that there are domains For example, you take x equal to just 1 inside here, so the two numbers are either plus 1 or minus 1. If you start at 1, this will give you the same result again, 3 by 2 minus half, which is equal to 1. That is fine. But if you start at minus 1, it will give you minus 1 as well. Okay, with both these signs will flip. So yes, both of them are solutions, but which one you will end up reaching is whether you started close to plus 1 or you started close to minus 1. So this is a multi-valued function. All these kind of things will happen, and you need to get some ideas about where to start, much more carefully in this case than in the single valued function case. So that is one feature, and the other feature is matrix version of this function is not known. This works for numbers, but and you can certainly do this also for a matrix. Multiplication is not a big problem, whatever it is. But how will you arrange the various terms so that they will give you the correct answer? And particularly, these various factors don't necessarily commute for matrices. And whether you can find an order which will give you the correct result, I don't know. Nobody has figured it out, or at least I have not seen the answer to this particular problem. And I thought about it a little bit, but my attempts didn't converge. One possibility is that if you can find out some initial guess which commutes with the matrix, then you don't have to worry about the order, because it will keep on producing new terms, but all the new terms will commute with each other because they are just polynomials. So that is not a problem. But even when you say that I want to find a square root, how do I find an initial guess which commutes with it? That is also not a trivial question. Maybe it can be done for specific instances, I don't know. But in general, it's something which one can, well, wonder about, see whether there is a efficient way to solve this problem, because square roots of matrices are needed in several applications. Okay. So yeah, this is as much as I want to say about all this linear algebra, and in the next lecture I will move to something else. I haven't quite thought about what will be the useful things related to it. Maybe one idea is kind of related, and that is this known as a variational method. Maybe I will talk about that. And the places where people are using them these days are problems in quantum chemistry. with some type of Hamiltonian which is given. So it's connected to this Hamiltonian simulation problems, but the emphasis on variational methods is not in finding the new state of evolution, but in terms of finding the ground states and its properties. So these are well related to the simulation problems in some ways. So what you want is if you want to design new kind of molecules and new kind of materials, you want to know what are the properties. And the properties which are important in practical situations are all the ground states of the molecules. We are not doing a what you call algorithmic evolution in the same sense that it is not a dynamics problem, it's more of a statics problem. Find a good molecule which has this property, and that molecule is stable. So yes, it starts with a Hamiltonian description, but asks a different kind of questions that you want to design lots of new materials. I mean, that is a huge industry in all kind of things, going from whether it is chemistry and biology to whether it is some engineering and physical systems. We want to explore all kind of things with what is the magnetic properties, what is optical properties, what are the what you call rigidity, the elastic properties, what are the electronic properties, conductivity, whatever it is. All kind of things are required to design new kind of materials. The question is, how do you find them? And then all you have is certain ingredients, which are some atoms, and you put them together and you want to get a new molecule. And the new molecule has to have some properties. And that problem here is to design those properties by tuning around some parameters in the Hamiltonian. And that is where all the variational stuff comes in. You change your parameters, some property changes, you trying to find a good fit to whatever you are looking for. Yeah, so this is again a generic problem in a lot of physics, all the way to biology kind of situations. And right now they are all simulations of some kind or the other, but done on a classical computer. The question is, can you develop quantum variational methods which can do the job more efficiently? And there, one of the fundamental features of quantum theory which appears is it has a natural variational principles. So if you have studied a little bit of quantum physics, you will know that there is a variational method. And can you adapt that variational method to this particular problem? That is the goal. So yeah, I will talk about this for the next couple of lectures.